Thank you very much. I hope you can hear me and hope you can see my slides. If not,
Yes.
please let me know. Great. All right. Well, I'm really excited to be here today to talk to you about how we go from pixels on a detector, like Juan was just showing us, to actual planets. So from the observations to the data processing to the investigations of possible weird effects to the discovery of planets. And in general, this process I'm going to go through has several steps. So I'm going to go through the pixel data itself. I'm going to go through light curves and how you can produce them, how you can correct for systematic instrumental effects, and how you can prepare them for looking for transits. I'll then go through the transit search process, which produces these threshold crossing events or possible signals where you might have a decline in brightness every so often, which would indicate that there's a planet there, but aren't quite well vetted to the point where we can say that they're good planet candidates. I'll then talk about how you go from these threshold crossing events to actual planet candidates, and then what additional observations and calculations are needed to actually take these candidates and take them from planet candidates into validated planets, ones that we're fairly sure statistically are real, and confirmed planets, the ones that are ironclad and the ones that we know have to be real because we see evidence for them in other ways. And this is a process that is pretty common to all of the different transit search missions that we do. I'm showing here Corot, Kepler, and K2, and the test mission. I'm not showing KOPS because it operates in a different mode. Usually KOPS knows where it's looking and knows that there's already a planet there because it's a pointed mission. So it's a little bit different from these two. The processes here are all fairly similar, but I'm going to focus on data from Kepler and from the K2 mission just because that's what I'm the most familiar with. So the K2 mission in particular is the second half of the Kepler spacecraft's lifetime. Kepler launched in 2009 with a full complement of 4 reaction wheels, which are these small gyroscope-like devices that keep the spacecraft pointing precisely in one direction. But after 2 of these failed during the course of the mission, Kepler was forced to abandon its original observation strategy and rely on just 2 of these wheels to point at different parts of the sky in a restricted form. When Kepler was operating in this mode K2, it still took images the same way that it always had. And these are what the images look like. This is a movie produced by K2 Flix, which is a nice piece of software written by Gert Berenson at the K2 Guest Observer Office at NASA Ames. And what you can see here is a star, and you can see that it's moving around a little bit because the pointing of the spacecraft was not perfect at that time. But overall, the star is staying fairly steady. And if we want to measure its brightness, all we have to do is select our favorite set of pixels and add up all of the brightness in each of these pixels together to get the total brightness, or a good approximation of the total brightness of our star. And when you do that for the K2 mission, you get something like this. So this is a light curve. On the y-axis here, I'm showing the relative brightness of this star as a function of time on the x-axis. And you can see that there appear to be these variations in brightness. Now, the question is, are these variations real? Are they astrophysical, something happening on the star itself, or are they caused by some instrumental phenomenon? And the answer is these are instrumental. So spacecrafts have systematic effects that manifest in their light curves. And interestingly, the dominant source is different for each spacecraft, just depending on how well it performs in its pointing, how well its focus is controlled, and whether there are any changes like the failure of reaction wheels that cause different behavior. So during the original Kepler mission, Kepler had such rock solid pointing that it didn't really matter at all how accurately it was pointed at the star for what the brightness was. Instead, the brightness systematics that were detected by Kepler were dominated by focus changes. So when the spacecraft would slightly heat up or contract due to different radiation environments, different mechanical pieces turning on in the spacecraft, it would heat up and change the focus and cause the brightness of the star apparently to change very slightly. So these hooks here, this is an image from Eric Pettigura's paper working on trying to remove these systematic effects. These hooks here are caused by the spacecraft reorienting itself and changing its thermal environment right after it downloaded data. You can tell because there's this gap here when the spacecraft was not observing and was instead pointing towards Earth so it could downlink data. And then you see these little ripples here. These are caused by heat from the reaction wheels as they try to maintain its pointing. And it has this very periodic cycle because the reaction wheels were keeping the pointing control on roughly a 2 or 3 day timescale. Here's another image that shows a zoomed in version of a light curve from John Jenkins's paper. You can see these little spikes happening every so often. These are actually due to an onboard heater that turns on and off during the mission. And in some stars, they're very prominent, and in some stars, they're not as prominent. And systematic correction, by comparing results from all of the stars to each other and trying to remove effects that seem to be common to all of the stars, can very well reduce them. TESS, on the other hand, is dominated by changes in the brightness or changes in the position of the spacecraft, so pointing jitter. It's relatively fast jitter, though, that matters. And it turns out that the jitter that happens is on timescales of just a few seconds, so that fast jitter that Juan was just telling us about. And what you can tell is if you look at the brightness of a star observed by TESS, which is this on the top panel here, you can see these little dips. And these dips correspond to times when TESS is moving back and forth within one exposure very rapidly. So even though the mean position of the spacecraft is very precise, the standard deviation of the position during each exposure increases. And that causes these brightness variations that we can see from TESS. Another big issue with TESS is that unlike Kepler and unlike PLATO, TESS is orbiting the Earth in a relatively close orbit. And as a result, you have light coming in from Earth and the moon, and those can severely affect your light curves and cause problems that you have to deal with. So this is an image of the 4 TESS detectors. And this blob here corresponds to our moon as it goes through the field of view, and this is our Earth. And you can see that the background of all of these images shows big changes in brightness caused by the 2 bodies moving nearby. This causes additional effects that we have to deal with in the light curves. It can create these weird transit-like effects when you have spikes in the brightness. So this is a light curve from TESS, which shows this weird double transit effect, which was a very interesting thing to find and was potentially something that we could have been excited about astrophysically until you realize that it's actually caused by the background. And you can see at the same time, there's a spike in the amount of light in the background of the images that's causing this. K2, as I mentioned earlier, was dominated by changes in the pointing because it no longer had 2 of its 4 reaction wheels to keep it steady. So K2 had these big excursions back and forth as it rocked around. So the way K2 worked is the spacecraft was no longer steady because it had lost 2 of its 4 reaction wheels. And if you look at an image from K2 on the detector, here's a star, here are the pixels. You can imagine that as the telescope drifts, the image of the star moves very slightly on the detector. And if you imagine that perhaps this pixel here is a little bit less sensitive than this pixel here, as more light from the star falls on this less sensitive pixel, you can see that the total brightness that you measure will slightly decline. But the nice thing about Kepler was occasionally, after it had rolled a little bit and drifted from its original position, it was able to fire its thrusters and bring itself back and start doing this whole drift pattern again. And when it did this, it traced out basically the same pattern. And that made it possible for us to correct these effects in the light curves. And in general, with these spacecraft systematics, you can often do a very good job at removing them and being able to get clean light curves despite these flaws in the underlying data. So when you do this for K2, you can go from a light curve that looks something like this with all of this messy jitter to something that looks much more like this, which is a lot easier for us to find planets in. So the next step in searching for planets is to remove low frequency variability. Stars are not constant in brightness, even if they have no planets. As star spots rotate in and out of view, as you can see in this very cool image from Rachel Rodenbacher, you can see changes in the brightness of the stars that look like these quasi-periodic sinusoids. I'm sure you heard all about this in Raphael Haywood's talk the other day in the radial velocity context. So if you want to search for planets, you need to account for these somehow. One of the simplest ways to do this is to just fit a spline, which is a piecewise polynomial function that can model all of these variations, divide it from your light curve, and give you something that looks like this. Now this is something where you can start searching for dips in brightness that happen due to transits. We do this with a couple of different algorithms. One of them is called the TPS, the Transiting Planet Search, that was developed by the Kepler team way back in 2002. Another one is coming into favor these days, is called the Transit Least Square Search. It's kind of a hybrid of the TPS approach used by the Kepler team and by this Boxley squares periodigram, which has been the go-to method for most people for the last couple of decades. But no matter what you do is you search for all possible different combinations of orbital period for a planet, time of transit, and transit duration. And you just do this massive grid search of all of these possible different configurations and see which locations, which points in this grid give you the strongest evidence for a planet signal. And in this case, I'm showing that there's evidence for a planet signal with a period of about 10 days. So if I take my light curve and I average and fold it onto that period, you can see something like this, where you see this pretty convincing looking dip. It's relatively low signal to noise. It's definitely not the prettiest transit I've ever seen, but it looks like it's probably real. And that's how you get a threshold crossing event, which is any possible transit signal in period, time of transit, and transit duration in a light curve that's strong enough for a transit search pipeline to identify. That doesn't necessarily mean it's likely to be a planet. You can get lots of them that are not planets, but planets are included among these threshold crossing events. So the next question is, how do you go from a threshold crossing event to a planet candidate? And there's a couple of different methods to do this, but one of them, the old tried and true method, is just for a human to look at each of them. So this is a movie that I made of myself, reenacting a large segment of my PhD thesis, where I spent time looking at different possible threshold crossing events from the Kepler mission. And by the time I got my PhD, I was pretty fast at this. So I was looking at each of these probably for about a second or so on average, and classifying them as either garbage caused by instrumental systematics, rotation signals that weren't properly removed, or planet candidates. But if you're looking at thousands and thousands, even if you go one a second, it takes a very long time to do. So we're working on trying to figure out better ways to make this triage process a little bit more effective, a little bit faster, and a little bit more painless for the people who are trying to discover planets from new missions. So this is work that was done by my former undergraduate student, Ann Datillo. She's now a graduate student at the University of California in Santa Cruz. And what she did is she took a neural network and she trained it on the classifications that I made during my thesis, and was able to achieve 98% accuracy, training her neural network to match what I had predicted or what I had labeled. And instead of taking about an hour and a half to do 3,000 signals, or an hour to do 3,000 signals, Anne was able to do it in about 20 seconds with 98% accuracy. So I wish I had this at the beginning of my thesis. It would have saved me a lot of time. So once you have taken these these threshold crossing events, you can give them even more scrutiny. And there are lots of different tests that you can do to make sure that what you're seeing is really a planet and not some sort of astrophysical false positive, like something like an eclipsing binary nearby that causes a signal that looks like a transit, but is not actually due to a planet, or some other instrumental systematic. So I produced lots of these different plots when I was working on the K2 mission, and used them all in different ways to figure out whether any given signal is a planet. This one looks pretty clean here. You can see there's a clear dip in the light curve. You can see that there's no difference between the depth of transits on the odd transits and the even transits, which would imply that it's actually an eclipsing binary with a period twice what we think it actually is. The transits all look consistent when you look at them individually over here in this plot. And these red dots here that indicate where the transits are happen all throughout Kepler's motion across the spacecraft, which implicates that they're likely not due to some sort of systematic effect. So this one I would say passes vetting and can become a planet candidate, which is a threshold crossing event that has passed this initial triage and additional vetting to identify false positives. Planet candidates, you can be fairly confident, and you can start looking at them and asking questions about the architectures of systems. So as an example, I'm going to go through this particular system called EPIC 248435473, which is a bit of a mouthful. This was a system that was published by Joey Rodriguez et al. Back in 2018. The interesting thing about, the thing that we want to do in this case is we have all of these different signals, which makes it a relatively interesting system. And we want to be able to rule out other more pernicious false positives, the ones that are not easy to rule out just by looking at the light curves. Sometimes you can have false positives that are so difficult to distinguish from real planets that you have to just hope that they're not true or calculate the statistical likelihood that these aren't the case. And that's the approach that most of the planets that have been discovered from transit surveys have taken. So one of the things that you want to make sure is that it's really a planet that's orbiting a star that's in your aperture and not a star with a background eclipsing binary nearby that's so close to it that we can't see it in our images, and this so close to it that we can't distinguish it from the transit photometry, or that it's an eclipsing binary itself. The other thing you have to worry about in this case is whether the signals you see are really caused by planets or if there's some weird looking instrumental glitch that causes a dip-like signal but is really hard to identify and which slips through your systematics correction and your triage and your vetting. So here's this example paper again, which has a very nice Astrobytes article if you're interested, because the interesting thing about the system is that the close-in planet is an ultra short period planet that's misaligned from the rest of them by about 20 degrees. So here's what the system looks like if you look in general in detail at the architecture. There's two candidate sub-Neptune planets that are each strongly detected. The detection significance here is about 110 sigma, and those are orbiting near a mean motion resonance. So every time this planet goes around 4 times, this one goes around 3 times, which causes dynamical gravitational interactions between the two. There's this planet here, which is the extremely short period planet that is out of alignment with the others. We detected this one at about 13 sigma confidence. And then there's these 3 other weaker signals. One of them is a Mars-sized candidate in a 7-day orbit, which we detected at about 10 sigma confidence. And then this one is a similarly sized planet in about a 6-day orbit, detected at 8 sigma confidence. And then this one is a sub-Earth-sized candidate near the habitable zone, detected at about 7 sigma. So there's a lot of possible signals, and they all have kind of different characteristics, which make it tricky to address the likelihood that each of them are real. So the first thing that you want to do once you have a system like this is take some follow-up observations from ground-based observatories. These tell you new things that you can't learn from transit observations alone. So we took data from the Palomar 200-inch telescope to get a near-infrared low-resolution spectrum. This helped us determine what the stellar parameters were for the system. We also can use information from missions like Gaia now. Back then, we didn't have any Gaia information to help us out. And this tells you if the star is what you think it is, a dwarf star where you could detect planets. If it were actually a giant star, then probably these planets would not be real. Otherwise, they would be so large, they would be the size of stars. We also took observations with optical telescopes to determine whether there were any large radial velocity variations. And it turns out in this case, there are no variations that we could detect. That's a good news because we took these at low enough signal to noise that we shouldn't have been able to detect any reflex motion due to the radial velocity signal of the planets. But if there were stars in the system, if it were a binary star, we definitely would have seen that. So we can confidently rule out that scenario. And as I said, we can confidently rule out eclipsing binary scenarios. We can also take advantage of work that was done decades ago to see if there's any possibility that there are stars at the current day position of that star that could be causing false positive scenarios. So this star is nearby. It has relatively high proper motion. And the proper motion is in fact so high that if you take an image look at an image that was taken in 1952, you can actually see the present day position of the star, and it is not covered up by the star itself. So that means that you can look for stars in the background that are moving very slowly, perhaps a giant star way back far away in the Milky Way, and determine that if there's nothing there, then that must mean that this could not be caused by a background star. So you have to be a little bit patient to do this. Your work to prepare for surveys like this will only pay off in about 60 years or more. But once you do that, it can really reap some rewards a long way down the road. You can also use modern imaging to look for really faint objects. So you can see here in this pan-stars image, this is the star in question, and this is a very faint detection of a star nearby. We're pretty sure that this can't be the source of any of the transit signals though, because if we take the pixels downloaded by Kepler and we look at them from a slightly smaller aperture, these outlines show the pixels that we selected. The red one was our default aperture, the default set of pixels. This blue one is the one that we tested out, if we move the aperture so that it excludes the star, we still see all of the signals with the same properties. So we can be fairly confident that the signals that we see are not coming from this faint star that we detected in modern imaging. You can do the same thing with adaptive optics imaging, and you can take a very close-up look very near the star and look for any other possible companions, often visual binary stars. In this case, we see none, which means that there's fewer chances that there's some object orbiting very closely to the star that is causing some or all of the signals that we see. So we can rule out this scenario fairly well. So the instrumental false positive scenario is a lot trickier. And there's no really good rule, but a general guideline is that if your transit signal to noise is more than about 10 sigma in Kepler, at least in K2, then you can be fairly confident that that's a real planet. If it's lower than that, then that's when you start to worry that some sort of instrumental false alarm could have snuck in. So in this case, we have 4 planets that are above 10 sigma, and we have 2 planets that are below 10 sigma. And this is fuzzy. This one, 10.6 sigma is really not that much above 10 sigma, but for the purposes of this paper, we called it good, and we decided to say that we could rule out the fact that all of these signals were caused by instrumental false positives, whereas these signals were a little bit more suspicious of them.
5 minutes.
There's a lot, or sorry?
5 minutes left.
5 minutes, okay, great. So there's a lot of other ways that instrumental false positives can sneak in. This is an unrelated system from the K2 mission, where you see this very interesting looking asymmetric transit, which for a few weeks we thought was potentially caused by some sort of exocomet or some sort of dust emitting object. But it turns out that this is actually image crosstalk from Saturn passing through the field of view of the Kepler telescope at this time and causing a negative signal to appear over here in the bottom corner of this cutout of the Kepler image where there are no stars. Here's another weird example. This is called KOI 6705 and was published by Eric Gaidos and his collaborators as a false positive back in 2016. You can see this transit signal here, which looks fairly strong and convincing. And indeed, it is due to some astrophysical explanation, but it's actually caused by the influence of a binary star. This is test data. Kepler actually didn't even download the data for this star. So we had to wait until the TESS telescope launched for us to confirm that this was indeed the source of this transit signal found by Kepler. And the weird thing here is that the signal is so far away, you would not necessarily expect it to be the cause. It's over 1,000 arc seconds away from the planet candidate down here, but they happen to line up in the same CCD column. And the effect of charge transfer inefficiency, which is something that the Kepler team refers to as column anomaly, makes it possible for the signal of this eclipsing binary to smear onto this potential planet host and cause this false positive signal. And in a lot of cases, these instrumental false positives can be very difficult to identify by eye. This is a very nice plot by Fergal Mullally and his team, who showed that this potential planet candidate up here, Kepler 452b, when you look at the transits one by one and when you average them together, it's very hard to tell without some pre-knowledge that this is not this is a planet and this is not a planet. We know that this is not a planet because this was a upside down transit signal. It couldn't possibly have been caused by a planet because it would have caused the brightness of the star to increase. But but the Kepler team was using these upside down signals to search for possible false positives and test their methods. And what they found is that when you look at just a lot of data, it's possible for you to see some really weird effects that look like transits even when they're not necessarily there. So future work on the pixel level is needed to confirm these week-long period signals. And this is very much an active area of work and something that needs to really, if we want to push to the lowest signal to noise candidates and find these long period small planets, we have to be able to figure out what's going on the pixel by pixel level. So once you have all of these pieces of information, you can calculate what's called a false positive probability. What's the likelihood that any given candidate signal is really a planet or is caused by some of these other false positive scenarios? There's a couple of different software tools to use this. One of the most commonly used is called VESPA, and that's what I'm demonstrating here. So VESPA is a Bayesian analysis. It takes priors based on the known occurrence rate of planets and the known properties of eclipsing binaries and likelihoods that you find something like that within any given region of sky. It then multiplies them by the shape of the transit and calculates a likelihood based on that, and multiplies those two together to give you a final probability. And in this case, we were able to show that this particular planet had a false positive probability of only about 1 in 2,000. And that's good enough to call it a validated planet in transiting exoplanet parlance. Another interesting thing is that you can learn more if you have multiple planets in the same system. It turns out that multiple planet systems are more likely to show up in the same part of the sky than false positives. And that's just because eclipsing binaries tend not to cluster together. They tend to be randomly distributed across your field of view. But planets can often be in the same systems. So if you see 5 or 6 planets all orbiting one star, that's a really good indication that those are real planets. So if you do the calculations, it turns out that for the Kepler mission, candidates in multi-planet systems are 20 to 50 times more likely to be planets than candidates in single systems. So you can take this number, you can multiply this number here by a factor of about 20, which really cuts down on your chances that this is a false positive. And then you can call it a validated planet, which is a vetted planet candidate with a calculated false positive probability less than some threshold. Often 1% or 0.1% is used. So these 4 planets we were able to validate. These 2 we were only able to remain as candidates because we were not confident enough that they were not caused by instrumental systematics to really elevate them to that next level of certainty. But sometimes you can go better and you can confirm planets, which is using some other piece of information or some other observations to show that this really is something with a planetary mass. One way that you can do this is with transit timing variations. These 2 planets here are good candidates for that because they're near mean motion resonance. So you should expect gravitational interactions between them. And indeed, that's what we see. If you look at the transit timing variations, the times at which the planets move in front of their star, you can see that they appear to behave in an opposite manner. This is a signature of interactions by the gravity of these 2 planets. So we were able to confirm those 2 planets. The other way to do this, which is often done, is to use radial velocity observations from telescopes like HARPS or HARPS North or Espresso in the future to confirm that you see a signal at the same orbital period that was detected by transits. This is a really difficult thing to do for the longest period planets and the small planets. So this is something that we would like to be able to continue doing in the future. We've had some success stories. This is showing Kepler 62f, which is probably the most confidently believed small long period planet detected by the Kepler mission. And one of the reasons that people felt so confident about it was originally detected with just 3 transits. And then after that detection, the 4th transit showed up and all of them looked good and all of them looked consistent. With TESS, we were sometimes able to take observations with additional telescopes because TESS has small apertures and it's easy to find a telescope that's larger. In the past, this role could have been done by the Spitzer telescope, which is what was happening here with TOI 700. But in the future, it could be done with KAOPS. So perhaps we would be wise to have some sort of additional mission on hand to be able to follow up observations from PLATO. I'm running out of time, so I'm going to throw up a few takeaways for the PLATO mission. And while people read this slide on their own, I'll take questions. Thank you very much.
Thank you, Andrew. Yeah, we only have 3 minutes for questions. We have some in the chat. So, okay, thank you, Andrew from Lokesh Mishra. Any comments on the effectiveness of the Kepler RoboVetter for automatic vetting on the transit signals?
The RoboVetter is excellent, and I would say is still the gold standard. My group is interested in working on neural networks to do this task. And those have advantages, but they also have disadvantages. Neural networks are able to kind of include more information from different sources in a more complex way and can more effectively mimic the reasoning that a smart human being would use. If you see, for example, a V-shaped transit, which wouldn't necessarily fail in the RoboVetter, and you also see a possible centroid offset, it can combine those 2 pieces of information together and say that this is most likely a false positive, whereas the RoboVetter might give that signal the benefit of the doubt. But its downside, this neural network downside compared to the RoboVetter, see many, many more observations for it to learn on. And it's hard for us to produce those data sets. So right now, the RoboVetter is excellent, and I would say the gold standard.
Okay, we have another question from Vikash Singh. I have a specific question regarding the 56-day period planet in the EPIC 2484 system from Rodriguez et al. I believe there were only 2 transits in the light curve. Can we validate it has a planet signal?
We did not when we were looking at this, and for that exact reason, because there were only 2 transits and they were fairly weak, and we weren't sure that they had to have been caused by a planet and not some sort of instrumental glitch. But yeah, if we were able to follow that up with Cheops, that would definitely help. The problem is that, as Juan was showing us earlier, Kepler had an aperture of 1 meter. Cheops only has an aperture of 30 centimeters. So you would still need several transits with Cheops to even get to the photometric precision of 1 transit with Kepler. And when you have a 56-day period, it takes a long time to do that. So that was the challenge with Kepler, is that it was the biggest telescope around. It's hard to come in with a bigger telescope and find, these very weak signals and confirm them. If this were TESS, then yes, Cheops would be an easy way to immediately confirm it. But just, this star is faint enough that it would be probably pretty challenging with Cheops to do.
Thank you. We have a last question on the chat, but we are running out of time, so I'll let you answer directly on the chat.